Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Shahid Latif, Associate Professor at Department of Computer Science, Sarhad University, Peshawar. Today we will learn lecture number 5 of Electronics 1 course. The course code for Electronics 1 is ELC216. This course is offered for several programs including BS Computer Science, BS Software Engineering, BS Telecommunication, BS Electronics. It is a 2-1 credit hour course, means that we have to cover 2-hour theory lectures per week, while there is 1 credit hour or 3 contact hours lab requirement per week. Some course details are such that we are in week number 3 of our course, and today we will learn lecture number 5. The topic of today's lecture is N-type and P-type semiconductors. In this lecture we will see that how an N-type and P-type semiconductors are formed. Similarly, we will also discuss that what are the majority and minority contents in N-type and P-type semiconductors? Before starting our new lecture, let's have a look on the previous lectures, lecture 1 to lecture 4. In lecture 1, we discussed the prerequisite for this course. The prerequisite courses for Electronics 1 include AC and DC circuit analysis. In that lecture, we discuss some important topics of these courses. Then in lecture number 2, we start our textbook chapter number 1. The title of chapter number 1 was Semiconductor Basics. In this chapter or in lecture number 2, we discuss the atom and the structure of an atom. Similarly, we also discuss the Bohr model for an atom, the atomic number of an atom, the electrons and shell in any atom, the valence shell and valence electron, and finally the ionization process. Then in lecture number 3, we start our lecture number 3 by discussing the classification of matter based on the conductivity, and we find that there are 3 types of matters: insulators, conductors, and semiconductors. Insulators are those materials which cannot conduct the electric current, while conductors are those materials which can conduct under the normal conditions, even on room temperatures. While the semiconductors are those materials which sits in between insulator and conductors in terms of their conductivity. Or we can say that semiconductor materials are those materials which can be used as insulator as well as conductors. Or in another way, we can define the semiconductor material such that semiconductor materials are those materials which have some properties of conductors and some of insulators. After discussing the classification of matter and the 3 classes, we discuss the energy bands. We also learn then what is valence band and what is the conduction band, and what is the energy gap between these 2 bands. We discuss the energy level diagram for all 3 types of matters, that is insulators, conductors, and semiconductors. Finally, in lecture number 3, we discuss the covalent bonds inside the silicon crystal. Then in lecture number 4, we start our lecture number 4 by discussing the current in semiconductor material, or simply conduction in semiconductor material. We discuss what is hole and what is an electron. The electron and hole pair is composed of an free electron and its vacancy in valence band, which is termed as a hole. We also discuss that when free electron loses its energy and fall back into valence band, it recombine with a whole. So this process, which is known as a recombination, is also discussed in lecture number 4. And finally, we discuss the two types of current in semiconductors. One due to the electrons, which is known as electron current or simply electronic current. And the other type is based on the hole. So that type of current which is because of hole is known as a hole current. Today in lecture number 5, we will start our lecture by discussing the N-type and P-type semiconductors. We know that pure or intrinsic semiconductors are neither a good conductors nor a good insulators. So we are in need to add impurities in these semiconductors. The process in which we add impurities in intrinsic semiconductors is known as a doping. As a result of doping process, the semiconductors can be either N-type material or P-type material. So here we will discuss that how N-type semiconductor will be formed and what are the majority charge carriers and minority charge carriers in N-type material. Afterwards, we will discuss that how P-type semiconductor will be formed and what are the majority charge carrier and minority charge carrier in P-type semiconductor material. A recommended book for this lecture as well as for this course include Electronic Devices, authored by Thomas L. Floyd. We are using 9th edition of this book. If you have any latest edition, it is also acceptable. Another version of this book, Electronic Devices, authored by Thomas L. Floyd, is electron flow version. Means that this book has two versions, the conventional current version and the electron flow version. Both of these books are recommended for this course, but majority of the contents of this course are taken from conventional current version. Now starting with the doping. As we know that intrinsic or pure semiconductors are generally poor conductors. Means that they cannot conduct electricity or electric current under the normal condition. So to increase their conductivity, we have to add the controlled addition of impurities, or we have to add the controlled amount of impurities. This process where we add impurities in intrinsic semiconductor material is called doping, or simply addition of impurities is called doping. The doping process increases the number of current carriers, which might be electrons or holes in semiconductors. The two categories of impurities are N-type and P-type impurities. Means that we have to add either the N-type impurity or the P-type impurity in intrinsic or pure semiconductors. The N-type semiconductor formation. Here we will learn that how we can form the N-type semiconductor materials. So as we know that pentavalent impurity atoms, those atoms which will be added in pure semiconductor material as impurity, having 5 valence electron in their valence shell. So to increase the number of free electrons in intrinsic silicons, we have to add such pentavalent impurity atoms. The common example for pentavalent impurity atoms include the arsenic, phosphorus, bismuth, and antimony. In our book, the antimony example is used as a pentavalent impurity atom. So we will also focus on it. In figure 1.17, each pentavalent or antimony atom forms covalent bond with 4 adjacent silicon atoms. As we discussed in previous lectures, that silicon atom in its crystalline structure is attached with 4 neighbor silicon atoms through covalent bonds. So here, by adding the pentavalent atom, we know that 4 of antimony atom's valence electron will be used to form the covalent bond with the silicon atoms. But the 5th electron or the 5th valence electron will be left as an extra electron inside the crystalline structure. And that extra electron becomes a conduction electron because it is not involved in bonding process. Here you can see that we have added a pentavalent impurity atom in a silicon crystal structure. An antimony impurity atom is shown in the center of this figure or of this crystal. Here the extra electron from the antimony atom become a free electron. We can see that the antimony atom is attached or linked with 4 silicon neighbors by sharing 1 electron with each. So 4 electrons of antimony atoms are shared with 4 different silicon atoms, but it has 1 extra electron, and that extra electron from the antimony atoms become a free electron or simply a conduction electron. So if we add 1 impurity atom, we will get 1 free electron or 1 conduction electron. If we increase the number of impurity atoms, the number of free electrons inside that material will also increase. As a result, we will know that silicon material will have electrons in excess. The pentavalent atom is also termed as a donor atom because it gives up an extra electron. That's why it is called a donor atom. Remember that the conduction electron created due to the doping process does not leave a hole in valence band because it is in excess of the number required to fill the valence band. Means that the conduction electron created by the doping process will not leave a hole behind in its valence band, because we know that electron is not generated, or that electron is not a free electron by leaving its valence band, but it was in excess due to the impurity atom. The majority charge carrier in n-type semiconductors are electrons, because we know that most of the current carriers are electrons. So silicon or germanium doped with pentavalent atoms in an n-type semiconductor. Here the N of n-type semiconductor stands for the negative charge on an electron, means that the n-type is representing the negative charge particle. So we can say that there are a lot of extra negative charge particles or current carriers as electrons. The electrons are the majority carriers in an n-type material. Similarly, the minority charge carrier in n-type materials are holes. Here we can say that although the majority of current carriers in n-type material are electrons, there are also a few holes that are thermally generated. Therm means heat, or we can say that those holes are generated due to the heat energy. So these holes are not produced by the addition of the pentavalent impurity atoms. The pentavalent impurity atoms are responsible for the generation of extra electrons. Holes are not generated due to the addition of pentavalent impurities, but the holes are generated due to the thermal energy. So we can say that the holes in an n-type material are now in minority, so they are called minority charge carriers. Now we will learn the p-type semiconductor formation, or we can say that how we can form p-type semiconductor material. Here trivalent impurity atoms, those atoms which have 3 valence electron, will be added as a impurity atom in intrinsic or pure semiconductor material. Reason behind the addition of trivalent impurity atom is that we are in need to increase the number of holes in intrinsic silicon. So for that purpose, trivalent impurity atoms are added. The common example which are used as a trivalent impurity atoms include boron, indium, and gallium. In our course, boron has been used as an example of a trivalent impurity atom, so we will also discuss the formation of p-type semiconductor in terms of a boron. Here in figure 1.18, each trivalent atom, for example boron, forms covalent bond with 4 adjacent silicon atoms. We know that boron has 3 valence electron, and the crystalline structure of silicon material is such that the silicon is attached, or silicon is bonded with 4 adjacent silicon atoms with the help of covalent bond. So the 3 of boron atoms valence electrons, or the 3 valence electrons of boron atom, will be used in the covalent bonding with the 3 silicon atoms. Since 4 electrons are required in that crystalline structure, so we can say that a covalent bond is missing in between the boron and the 4th silicon atom. As a result, the deficiency of electron will occur, and that deficiency of electron results in a hole when each trivalent atom is added. So we can say that due to the addition of one boron atom, we will have one hole in that semiconductor material. If we increase the number of boron impurities, the number of holes in that semiconductor material will also increase. If we add 100 boron atoms, we will have 100 holes in that material. If we add 1000 boron atoms, we will have 1000 holes in that material. And due to the majority of holes are in excess in semiconductor material, so that type of semiconductor that type of semiconductive material is known as a p-type material. Here p is representing the positive charged particles, and we know that holes are positive in nature, so in terms of holes, this semiconductor material is known as a p-type semiconductor material. Here in this diagram we can see that the atomic structure of silicon is such that the center silicon atom is attached with four different or four neighbor silicon atoms. Even when we add a boron atom as an impurity atom, it will adopt the crystalline structure of the silicon or the silicon crystal. So when trivalent impurity atom in a silicon crystal structure is added, for example a boron, the three neighbor atom or three silicon atom will share their one electron with boron through covalent bonding. But the fourth one silicon atom, boron atom, has no extra or no valence electron which it can share through covalent bonding with the upper silicon atom. As a result, a deficiency of electron is occurred, and that deficiency of electron is known as a hole due to the boron atom. Now the trivalent atom which we add in our semiconductor material can accept an electron, and due to this acceptance of electron it is referred as an acceptor atom, while the pentavalent atom can provide an electron, so it was referred as a donor atom, while the trivalent atom can take an electron, so it will referred as a acceptor atom. Remember that a hole created by this doping process is not accompanied by a conduction free electron, means that the hole created due to doping process is not associated with the free electron or with the conduction electron. The majority charge carrier in p-type semiconductor material include the majority charge carriers in p-type semiconductor material are the holes. We know that from the previous discussion that since most of the current carriers in p-type material are holes, so a silicon or germanium doped with trivalent atom is called a p-type semiconductor. The holes are the majority charge carriers in p-type material. On the other hand, the minority charge carriers in p-type semiconductor material are electrons. You will see that in p-type material we have a lot of holes, but there will be some or few electrons which will be termed as a minority charge carriers. Here we know that in minority charge carriers, although the majority of current carriers in p-type material are hole, means that holes are used as a current carrier particles, and these holes are in majority inside the p-type material. But there are also a few number of conduction band electrons, or simply we can say that there are also few electrons. These electrons are created when electron-hole pairs are thermally generated. Means that these free electrons or conduction band electrons are thermally generated electrons. And we can also say that these conduction band electrons are not produced by the addition of the trivalent impurity atoms, as it was in case of an n-type semiconductor material. We said that in n-type material the holes are minority charge carrier, but that holes were not generated due to the addition of the impurity atoms, but that holes were generated due to the thermal energy. Similarly, in p-type material, minority charge carrier are electrons, and these electrons are not produced by the addition of the trivalent impurity atoms, but these electrons are thermally generated. So the conduction band electrons are simply the free electrons in p-type materials, can be considered as the minority charge carrier. In summary, we can say that n-type material has two types of current carriers. In n-type, majority current carriers are electron, so these charge carriers will be known as a majority charge carriers, while holes holes are in minority or in less number, so they will be considered as a minority charge carrier. On the other hand, in p-type semiconductor material, there are also two types of charge carriers. One type of charge carrier is in majority, which are holes. So the current in p-type material will be due to the holes, and the holes are considered as majority charged particles in p-type material. On the other hand, there are few thermally generated electrons as well in p-type material, and these few thermally generated electrons, which are lesser in number, are termed or referred as minority charge carrier. Thank you very much. That is all for today. If you have any question or any query, feel free to contact me on shahid.csit@soot.edu.pk. Thank you very much.